I'm Adam from RFOXiA from our real lab. Today's question: can a Bluetooth network operate completely without cellular infrastructure, internet or satellites, and actually be useful when those things disappear? Let me start with the fact that the wireless industry finds inconvenient. Every communication system most people rely on, cellular, satellite uplink, standard Wi-Fi, depends on infrastructure that belongs to someone else. You are a user of that infrastructure. You are not in control of it. And the moment it fails for any reason, your communication fails with it. This is not a theoretical concern. It is a documented pattern. Floods knock out cell towers, earthquakes sever fiber, congestion during emergencies collapses the networks precisely when demand is highest. Governments can shut down cellular service at will in a defined geographic area. None of these scenarios are rare. They happen regularly in real places to real operators who needed their comms and did not have them. The alternative is a network that does not depend on any of that. A network where the hardware in your hand and the hardware on your robot or drone or sensor node are the entire infrastructure. Nothing in between, no subscription, no tower lease, no single point of failure you do not personally control. This is what point-to-point BLE actually is when you design it properly. In a point-to-point configuration, two modules communicate directly. One transmits, one receives. The range is determined by transmit power, antenna design, and this is the part most people get wrong, receiver sensitivity. Sensitivity is the ability to detect a weak signal. It is measured in dBm, and lower numbers mean better performance. The Multinav Pro Plus BLE module operates at -104 dBm sensitivity. That number represents the floor of what the receiver can distinguish from background noise. Most commodity BLE chips operate around -90 to -95 dBm. That 10 decibel gap sounds small. It is not. Every 3 dBm represents a doubling of detectable signal power. The difference between -95 and -104 is roughly 6 times more sensitivity. That is the physics behind the range numbers. I did not shout louder. I learned to hear better. Now extend this to mesh topology. In a mesh network, each node is both a receiver and a relay. A signal originating at node A can pass through node B and arrive at node C, even when A and C have no direct line of sight to each other. This is how BLE mesh allows communication across distances and around obstacles that would stop any point-to-point link. In disaster response specifically, this is not a convenience feature. It is the difference between coordinating a search team and not coordinating one. Field robotics has the same requirement stated differently. A ground robot operating in a collapsed structure, a subterranean space, or a dense forest has no guarantee that its operator maintains direct line of sight. Mesh relay nodes deployed ahead of the robot or mounted on secondary platforms maintain the communication chain regardless of the physical path. The operator does not need to move. The network routes around the obstacle. For remote deployments, environmental sensors in wilderness areas, monitoring equipment in agricultural land with no cellular coverage, research instruments on high-altitude platforms, the mesh provides something even simpler, the ability to exist at all. These locations have no towers, they never will. The only viable network is the one you bring with you. I want to address one question that always comes up, which is latency. BLE is not a zero latency protocol. At 2 megabits per second data rate with properly configured connection intervals, practical latency for control commands is in the range of 10 to 30 milliseconds depending on hop count and congestion. For drone telemetry and sensor data streaming, this is entirely acceptable. For applications requiring sub-millisecond precision, BLE is the wrong tool, and I will tell you that directly rather than let you find out in the field. The RFOXiA Connect app completes this architecture on the software side. The controller interface communicates with the BLE module over standard Bluetooth from your phone. The module then handles the long-range link. Your phone never touches the internet for this to work. The map, the sensor data display, the control inputs, all of it runs locally. So that is the architecture. So point-to-point mesh, receiver sensitivity, and what it means when infrastructure disappears. Now let me show you the actual hardware that does this. This is the range claim made physical, up to 50 kilometers between two modules completely independent of towers or internet. For drone control, ground robotics, or remote sensor networks, this is the link that keeps working when everything else does not. 2 megabits per second over a link that long is not a default BLE capability. That data rate supports real-time telemetry, sensor streaming, and control commands simultaneously, without the latency that typically appears when you push BLE hardware past its intended operating envelope. The STM32WB07 CCV6 runs both the BLE stack and your application code on a single core. This matters for mesh deployments where each node needs to manage routing logic independently without an external processor adding cost, size, and failure points to every node in the network. 57 by 47 millimeters with standardized mounting holes, a node small enough to embed in a relay housing, mount to a drone frame, or integrate into a field sensor enclosure without redesigning the chassis around the radio. That constraint was intentional. The mesh network becomes more capable as you add modules from the same ecosystem. GNSS for verified node positioning, sensors for environmental data at each relay point, motor and battery management for mobile nodes. Each additional module is a capability the network inherits, not a separate system to integrate. The RFOXiA Connect app is the command layer for the entire mesh. Map view shows all active nodes with live GPS positions. Sensor panels display real-time environmental data from every node in range. Control inputs route through the BLE link without touching any external server at any point. BLE Chat uses the same mesh infrastructure for text and data between operators. In disaster response or remote field operations, this is not a secondary feature. When cellular is down, the ability to pass text between team members over the same hardware running your sensor network has direct operational value. The firmware running on this module is fully accessible and modifiable. SWD programming interface, open source code base, and the AI firmware builder in RFOXiA Club if you want to describe your application in plain language and start from working code rather than a blank file. The RTC crystal handles timing synchronization across distributed nodes. In a mesh where multiple sensors are logging data simultaneously, consistent timestamps across the network are not optional. Knowing that two readings from different nodes are temporally aligned is a basic requirement for the data to be meaningful. Mesh, no server, no routing through a data center somewhere, the message goes from module to module and arrives. The practical implication of all of this is that the network described here, long-range, mesh-capable, infrastructure-independent, is not experimental. It is certified, it is shipping, and it costs $59 for 2 modules. The gap between what this should cost based on the underlying technology and what it actually costs exists because the industry decided long-range wireless was a premium category. I disagree with that decision.